This video talks about Newton's law of gravitation. Our current understanding of the force of gravity begins with Isaac Newton. Another of Isaac Newton's many accomplishments was the formulation of the Universal Law of Gravitation. The law is very powerful and fundamental. Without it, for example, we would not understand the cause of tides or know how to put satellites into particular orbits around the Earth. This law allows us to analyze the motion of planets, comets, stars, and even galaxies. The word universal in the name indicates the importance of the law, but for brevity, it is common to refer simply to Newton's law of gravitation or the law of gravitation. Newton's law of gravitation in mathematical form gives a simple relationship for the gravitational interactions between two particles or point masses m1 and m2 separated by a distance r. Two particles, m1 and m2, separated with a distance r. This distance between them is r. Basically, every particle in the universe has an attractive gravitational interaction with every other particle because of their masses. The forces of mutual interactions are equal and opposite, forming a force pair as described by Newton's third law. So the first particle m1 attracts the particle m2 with the force F on 2 by 1, or second particle with mass m2 attracts m1 with the force m on 1 by 2. But they are equal and opposite to each other, so we can write F1 2 equals negative F2 1. Newton proposed that every object in the universe attracts every other object with a force that has the following properties. Number one, the force is inversely proportional to the square of the distance between these objects. So we write the force is inversely proportional to the distance square between them. The force is directly proportional to the product of the masses of the two objects. So the force directly proportional to the masses multiplied by each other. Hence, Newton's law of gravitation has a form of F is proportional to m1 m2 over r squared. And it is expressed as an equation. If you want to express this as an equation with a constant of proportionality, the magnitude of mutually attracted gravitationally attractive force Fg can be written as Fg equals G, capital G, times m1 m2 over r squared. So where G is the universal gravitational constant, universal, and it has a value of 6.67 times 10 to the negative 11 newtons times meter square over kilogram squared. This constant is often referred to as a big G to distinguish it from the little g. The acceleration due to gravity. But here's the question: how did Newton come to his conclusions about the force of gravity? Legend has it that his insight came after he observed an apple fall from a tree to the ground. Newton had been wondering what supplied the actual force, centripetal force, to keep the moon. When I say centripetal, I mean center-seeking force, to keep the moon in orbit, and might have had this thought: if gravity attracts an apple towards the earth, perhaps it also attracts the moon, and the moon is falling or accelerating towards the earth under the influence of gravity. Whether or not the legendary apple did the trick, Newton assumed that the moon and the earth were attracted to each other and could be treated as point masses, with their total masses concentrated at their centers. Newton considered the nearly spherical Earth and the Moon to be point masses located at their respective centers, and it took him some years using mathematical methods that he developed to prove that this is the case only for spherical homogeneous objects. So this law applies to the force between two spherical objects if r is the distance between their centers. Two spheres and their centers, one has a mass m1, the other one has a mass m2, and all it matters the distance between the centers. Let's call it r. Then these two spheres attract with each other with the force F on 1 by 2 and on 2 by 1. During his lifetime, Newton left his relationship in the form of proportionality, just because he didn't know what's the value of G. Only 71 years after his death, an English physicist, Henry Cavendish, used the sensitive balance to measure the gravitational force between separated spherical masses. And he found the value of big G, knowing the force R and the masses of these objects. Now, when the law came in an equation form, we can analyze this by saying that this law, gravitational force between two objects, are actually represented with the inverse square, and because of the distance appears squared in the denominator. What does it mean? It means when you double the distance between two objects, so double r, what happens to the gravitational force? Force between them, two masses, decreases 4 times. This mathematical form, inverse square, we will see again, so it is worth our time to explore it in more detail. Mathematically, we say two quantities have inverse square relationship if y is inversely proportional to the square of x. Or in equation form, it would be y equals some constant a over x squared. And that is y is inversely proportional to x squared. And if we make a graph of this equation, of this relationship, put the x on the horizontal and a y coordinate system on a vertical, and let's say we have 1, 2, 3, 4 values for x. Then the y for x equals 1, the y will be a. X equals 2, y will be a over 4. For 1/2, when x is 1/2, y will be, if you plug it in, y will be 4 times a. So let's find these points. This would be right here. Okay, and here. And so you can continue on, and the graph you will get for this equation will be something approximately looking like this. So we can look at this graph and say, if you double the x, you decrease y by a factor of 4. If you halve the x, you increase y by a factor of 4. If you increase x by a factor of 3, you decrease y by a factor of 9, and so on. Generally, if x is increased by a factor of c, then y decreases by a factor of c squared. So let's put down here, decreases by a factor of c squared. If x decreases by a factor of c, then y increases by a factor of c squared. Now we can calculate the acceleration due to gravity at a particular distance from a planet by using Newton's second law of motion and the law of gravitation. So the magnitude of acceleration due to gravity, which will generally be written as ag at the distance r from the center of spherical mass m, is found by setting the force of gravitational attraction due to that spherical mass equal to mass of the objects times the acceleration of g, or the weight. This is the net force on an object of mass m that is at the distance r. So mass m right here. So I could say the force that is the sphere, this force that is sphere is pulling the object with the mass m, gravitational, should equal to mass times acceleration. That's the net force. That's the only force acting on this little mass right here. And what I wrote, this is according to Newton's second law. Now the gravitational force between these two these two objects, sphere and a tiny object m, would be written g little m times big M over r squared, and that equals little m ag. So the m's will cancel out, then I would get acceleration due to the gravity at any distance from the Earth that has a value of r would be equal g times m of that sphere over r squared. Notice that this ag the acceleration due to gravity is proportional to the inverse r squared. So the further away an object is from the planet, the smaller is the acceleration due to gravity, and the smaller the attractive force mag on the object. The force is directed towards the center of the planet. So this expression can be applied to the moon or any planet. For example, taking the Earth to be a point mass ME located at the center of the radius of the Earth. So let's say this is the sphere is our ME. And actually, let me draw a new picture here. Okay, here is the Earth and a little mass m near the Earth's surface. So the radius of the Earth will be the distance between the mass of the Earth, between the center of the Earth and the mass m object. Or because, well, from our expression, you know that acceleration due to gravity doesn't depend on a mass at all. So then I can write acceleration due to gravity on the Earth, for the Earth, not on the Earth, equals g times mass of the Earth divided by radius of the Earth squared. And this expression has several interesting applications. First, it reveals that taking g to be constant everywhere on the surface of the Earth involves the assumption that the Earth has a homogeneous distribution of mass and that the distance from the center of the Earth to any location on its surface is the same. These two assumptions are not exactly true though. Therefore, taking g to be a constant is an approximation, but one that works pretty well for most situations. Also, you can see why the acceleration due to gravity is the same for all freely falling objects, that is, independent of the mass of the object. The mass of the object doesn't appear in my equation here. So all objects in free fall accelerate at the same rate. The mass, finally, if you are observant, you will notice that our equation can be used to compute the mass of the Earth. All of the other quantities in the equation are measurable and their values are known. So mass of the Earth can be calculated. This is what Cavendish did after he determined the value of g experimentally. Now, the acceleration due to gravity does vary with altitude as a distance h. So let's say if you have your object higher at a certain height, say from here to here, call it h, and your object is here m, then the distance will be re plus h, right? So this would be your actual r from here to here. Then we can write acceleration due to gravity at a certain altitude equals g times mass of the Earth over re plus h squared. So for the moon, we can write g m, or moon, let's just write the whole word, equals g gravitational, universal gravitational constant times mass of the moon over radius of the moon squared. So we can generalize this by writing g of any planet equals universal gravitational constant times the mass of the planet over the r planet square. Thanks for watching. Stay tuned for more to come.